After we learn about the QQ plot, we need to understand also some other basic statistic. We call it the correlation. In this section, we have the correlation analysis on the nominal data. Do you still remember what is nominal? Name. Okay. Thank you. So we can see the nominal, something like, yeah, city name, okay, or maybe some categories, okay. We call it the categorical data. And the formula is like this one: observed minus expected power of 2 divided by the expected, and we will do the summation. In this case, the larger value, the larger of chi-square value, the more likely the variables are related. So we have the keyword related. The cells that contribute the most to the chi-square value are those whose actual count is very different from the expected count. So if we have this observed value, and if the expected value, if they are so different, then the chi-square value might be very high. So the word here is correlation. So the correlation does not imply causality. What does it mean? Let's say I have two variables. Let's say the number of hospitals and the number of car theft in a city are correlated. Because of the chi-square, okay, we can see they are correlated. But can we say something like, okay, maybe because the car theft is the criminal. Okay? Because of the number of criminals high, then people go to hospital more. So that's why the number of hospital is also high. Can we say like that one? No. Okay. Because it is only to show the correlation, but no causality. Okay. Do not make any cause and effect on those data. Okay. Because maybe both are causally linked to the third variable. Maybe because of the population. When the population increase, yeah, of course, they need to have more hospitals. Of course, they need to have more police office, because there will be also a lot of criminals. Okay? So there can be some situation with the third variable. So when we have the high correlation value, we can just say that the two variables are correlated. That's all. Okay. Now let's see example. We have a coin. You know coin? Coin, we will have only two sides, front and rear, or sometimes we call it head and tails. So we can record the number of head and tails. For example, I toss the coin 100 times, and among the 100 times, I have 48 heads and 52 tails. Now, I would like to check whether there is a correlation between the head and the tail. Is there any correlation between the two sides of the coin? Okay. So if I have 100 times, it's obvious that the expectation should be the same, 50-50. So the head observation value is 48. We expected 50 times. The tails 52 times. We expect 50 times, 50-50. So is there any correlation between head and tails? We can check with the numbers. O minus E, observed minus expected. So 48 minus 50, it is minus 2. Power of 2, it becomes 4. And we want to do this formula. Observed minus expected, power of 2 divided by expected. So 4 divided by 50 and 0.08. The second one is also 0.08. So the chi-square is 0.08 plus 0.08 and the value is 0.62. Is it high? Can we say those two data have correlation? No, because it's very small value, 0 point something. Okay. Let's see another example. We have like science fiction, not like science fiction. And we have play chess and not play chess. Maybe the data is something like in the table. The person 1, he liked, maybe this is the science fiction. And this is about the chess. So the person 1, he liked the science fiction. It's true. And he also played chess. So it is true. Maybe the person number 2, he doesn't like science fiction. So false. He doesn't play chess. So it is false. So we can have many data and we can calculate. The person who likes science fiction and play chess, we have the number 250. So our data, we have 1,500 data. So among 1,500, 250, they like science fiction and they play chess. 200 data or 200 people like science fiction and do not play chess. 50 people, they do not like science fiction, but they play chess. And 1,000 data or 1,000 people do not like science fiction and do not play chess. Okay, so this is the data. Now, I want to know whether there are correlation between those two columns. The numbers, the chi-square calculation, numbers in the parentheses are the expected counts. So I know the actual data is 250, but actually I'm expecting only 90 for this data. I know the actual is 200, but I'm expecting 360. Okay. So that's the meaning by the numbers in the bracket. Now, when we want to calculate the chi-square, we need to see the observed value, which is 250, minus by the expected value, 90, and divided by 90, which is the expected value. And then we will do the remaining data. We have the not like science fiction, which is 50, and 210 is the expected. We have 200, which is like science fiction and not play chess, and 360 is the expected. 1,000 is the actual value and 840 is the expected. And the result is this one, 507.93. So, is there any correlation between these two variables? We can see in the previous example, the numbers is 0.16. So it's very small. Here, number is 500. So it's very big. Based on the definition, the larger the chi-square value, the more likely the variables are related. Because we have a very big number like this one. So it shows that like science fiction and the play chess are correlated in the group. So we can see the correlation is on the chi-square values. Yeah. There is no criteria, okay, but we can see later if we have a lot of variables. Let's say now we have only 2. What about if we have 1, 2, 3, 4, 5? Okay, let's say we have 5 attributes. If we want to select which attributes are the most correlated, then we will sort the values. So the highest means the most correlated. The lowest means not correlated. So usually we use just sorting. That's why there is no criteria. If it is very small value, maybe we can just exclude because the data has no correlation. Okay. Thank you. Thank you for good question. Any other questions? Okay, then let me continue. This is the example for nominal data. Nominal is categorical data. Now, what if we have numerical data? We can measure the correlation with correlation coefficient and the method called person product moment coefficient. This is the formula. The idea is just to find the relationship between the two values. Let's say we have A, this is the variable A, and this is the variable B, and we want to find out the difference, whether AI, which is the value minus by the average of the attribute A, and BI minus with the average of attribute B, and we will do the summation and we will divide it with the standard deviation of the A and the standard deviation of B multiplied by the number of the data. Or we can also use this formula. So A and B, they are two different columns or two different variables. If R means the correlation analysis, is greater than 0, then A and B are positively correlated. It means when A increase, B also increase. The higher of R value, it has the stronger correlation. So the R, the maximum is 1. So if it is 1, then it is very strong correlation. If it is 0, it is independent. If it is less than 0, it is negatively correlated. For example, there is a an agriculture research organization. So they are testing a particular chemical fertilizer. Fertilizer, I guess, you know, when you want to make plant, okay, when you have plant, you will put some fertilizer to make the plant grows. Okay. So this agricultural research center, they want to know if this fertilizer affect to the growth of the food supply or not. If they put more fertilizer, they want to know if the food supply increase or not. Now they have the data. X is the fertilizer, the amount of the fertilizer. Y is the amount of the food supply. When they put 2 units of fertilizer, they have the data that the food supply is 4 units. When they have 1 unit of fertilizer, when they put the 1 unit fertilizer, the food supply has 3 unit production. Then they have, when they put 3 units of chemical fertilizer, the food supply is 4 units in the production. Okay. Now, is there any correlation between the fertilizer and the food supply? So we need to calculate. Here's I put the calculation. First, the sigma x. The sigma x is the summation for all the data. The sigma y is the summation of the y. And then we have x multiplied by y. X multiplied by y is x just multiply with y. 2 multiplied by 4, 8. 1 multiplied by 3, 3. 3 multiplied by 4, 12. And so on. We will do the summation. And then we have the x power of 2. So 2 power of 2, 4. 1 power of 2 is 1. 3 power of 2 is 9. And so on. And we will do the summation. We also do for the y power of 2. Now we input into this formula. This formula is n sigma x multiplied by y minus and blah blah blah, like this one. So we can just input all those numbers into here. N is 7, and the sigma x multiplied by y is 93. So we put here. And then sigma x is 20 and sigma y is 30. And then, yeah, we just input all the numbers here. So after we do the calculation, we get the value R is 0.811. Is it big or not? Big? Yeah. Because it is nearby 1. Okay. As I mentioned, the maximum is 1. It is nearby 1, so we can say that there is a correlation between the fertilizer and the food supply. You can use the correlation function in the orange. You can select the widget correlation. So you can see petal length and petal width shows a positive 0.963. So it is a very high correlation. Petal length and sepal length is plus 0.87. Petal width and sepal length is 0.8. Okay. But the remaining is showing negative correlation. petal length, sepal width is minus. Petal width, sepal width minus. Sepal length and sepal width minus. Okay, there can be something like this one. So the idea is something like this. When you have the visualization, it is more clear to see the correlation. If the line is like this one, then it is negative correlation, or the R is like -1. If the line is here, then the R is 1. If it is 0, we cannot see any patterns. So the value that we get before is 0.8, so something like this one. Then it is positively correlated. Note that the scatter plot will show the correlation value is from -1 until 1. I have put this one. -1 is the minimum and +1 is the maximum. You can see this also based on the scatter plot. Okay, you can select the widget scatter plot. So I think I put this one. Okay. So with the scatter plot, if I look at the correlation, the highest value is in between petal length and petal width. So I can do the scatter plot, and let's check the petal length and the petal width. And you can see that, yeah, it is increasing. The higher value of the petal length shows the higher value of the petal width. That's the meaning. If you want to make sure more, you can click this one, show regression line, and it will show the R value. Here, the blue color is the R value for the blue, which is Iris setosa. The green color is the R value for the Iris virginica. And the red is the Iris versicolor. What about the black? The black shows the whole population. Okay, so for all values, for those 3 flowers, then it shows 0.96. So it has a high correlation for all of the flowers. As you know, we can have the positive correlated data. When the X increase, the Y also increase. We can have negative correlated data. When the X increase, the Y decrease. That's the meaning by negative correlated data. But there can be a situation when the left half fragment is positively correlated until half, the right half is negative correlated. So it goes down. That's possible. For example, we have the product life cycle. So a product may be like smartphone. After you buy the smartphone, maybe in the current years, 1 year, 2 years, 3 years, it's getting popular. But after 3 years, the product is not popular again because there will be a new version, there will be a new product. If we see this kind of plot, then it is uncorrelated because there is no such pattern. The x increase here, but there is no pattern if y increase or not. The x increase, but the range is here. When the x increase, the value is still in this range. So there is no pattern. That's why we call this is uncorrelated data, not correlation. Okay, just giving you this learning chart. What is the purpose to do analysis on the central tendency? We want to check the data characteristics. Okay, we can see the minimum, we can see the maximum, we can see the median, the mode, the mean, and we can see the dispersion of the data. Okay. What are the components of the 5-number summary? Okay, minimum, Q1, median, Q3, and maximum. Okay, those are the 5-number summary. A box plot can represent 5-number summary. True or false? True. Okay. Yeah, this is very easy question. Hopefully, yeah, you can review other facts. So let's move to the next PowerPoint. We are going to discuss about data visualization. For this data visualization, there are some parts that might be not that very useful for you. So I got this material from the book. I bring the books. If you have interest to buy the books, yeah, this is a bit old version of the book, but it is still relevant. Okay? So I took all those things from this book. If you do not buy the books, yeah, you can just refer to my PowerPoint. Okay? The basic of visualization. Okay, so we will check what is the basic of visualization, and we can do some exploratory data analysis with visualization. Data visualization. Why do we need to do data visualization? You know that data visualization means we want to show the data in a graph. We want to show the data in the plot, maybe in terms of lines or yeah, with some pictures. Why? Why do we need to do the data visualization? We need to gain some insight. We need to get some information. And with mapping the data into graphical, we can get some idea. And it will provide qualitative overview, especially when you have large data set. So your data now is only 20 data or 150 data. But what if your data is 1 million data? It will be very confusing. So you need to plot it. And we can search some patterns, trends, structure, irregularities, relationships among data. And we can find interesting regions and suitable parameters for further quantitative analysis. These are some categories about the visualization. Let's consider the basic visualization first. Bar chart. I think this is the most common chart. It is best used for reading numbers accurately from the chart. It can compare individual bars to each other, and it explores overall trends across the categories. Let's see. This is male and female occupation from the 1881 census of England and Wales. Okay, so it's very old data. And we want to see the blue color is male and the orange color is female. And we want to see in the respective of the occupation. In the old days, yeah, they don't have many occupation like these days. Yeah? So they have like unknown occupation. So it is no definition. Person without specified occupation. Person working and dealing in general, maybe organization. Person working and dealing in various mineral something. Yeah. Person working and dealing in dress, and so on. So we want to see how many person with a certain occupation. The bar chart can help us to understand. Oh, the male works on the agriculture. Most male works on agriculture, and most female has unknown occupation. Maybe they cannot define their occupation at the time. So the data here means we can plot one or more text or categorical variables and one numerical variables. The numerical here is this one, the numbers. So we can see it is about 99 or 95 maybe. And this is maybe about 75. Okay, so there is a number that can be represented in the bar chart. Histogram. So we can see that it's similar with bar chart. So what is the difference? With just numbers? Okay, that's good. So when we use the bar chart, usually we want to represent the categorical variables. When we use histogram, we want to represent continuous or numerical variable. Let's say this is the height of black cherry trees. So maybe I have the data. The tree number one. The tree number one, I can measure, okay, the height is 62. The tree number two, I measure the height, okay, the height is 70 feet. The tree number three, so okay, the height is 63, and so on. So we can categorize those numbers into bin 5. Okay. So what you already saw before in the orange, we can define the bin. So the numbers between 60 and 65, we have 3 trees. The height in between 65 and 70, we have also 3. The height in between 70 and 75, we have 8, and so on. So this x is the continuous variable or numerical variable. That's why we call it histogram. Okay. to show the density and the distribution of continuous numerical data. Note that bar chart plots categorical data. Okay, that's the difference between histogram and bar chart. Scatter plot. Scatter plot, it is best used for showing one variable affects the other, or for showing precise data dense visualization, correlation, and clusters between two variables. Now, this is a data about tips. Do you know tips? If you go to USA, or maybe in some European countries, when you visit restaurant, you need to pay some tips for the waiter. Okay? So if the waiter give you a good service, you may give more tips. Okay? So the tips, it depends on you, how much you want to give. So this data is collected by the waiter. So the waiter check how much tips given by the customer, and also he collect the total bill. So waiter knows how much the customer pay for the bill and how much tip given by the customer. They want to see whether there is a correlation between the total bill and the amount of tips. And this is the plot. So can we say that the higher bill means the higher tips? Somehow, yeah, we can see something like this one. Okay, there is a progress. And this plot, it shows in the blue and the orange color, which is representing the dinner and lunch. So the blue is the dinner and the orange is the lunch. It seems that the blue color or the dinner, yeah, is in the top, or is the maximum, or is higher than lunch. What can we see from here? The data is two numerical variables. Okay. Bill, it is in US, so $10 or $20 or $30 and so on. And tips, and this is also in dollar, $2, $4, $6 and so on. When a third numerical variable can be added, it will create a bubble chart. So the third variable changes the size of the dots. So what does it mean? Let's see in the audience. So in the orange, let me make another file. First, I would like to show you the bar chart. Okay? We can show the bar. Okay? There is a bar plot. Oh, sorry. What is this data? Okay, this is the person head with. Let me change to iris. Okay, the bar plot. Why it represents something like this? Based on the definition, the bar plot should be for the categorical data. But in our data set, in the iris data set, there is no categorical. The category is only the iris or the flower. So in this case, they will plot all the values. So the categories is the instance. One row means one category. That's why it shows that all the data has been plotted in this bar plot. You can see the blue color is the iris setosa. So there are 50 data. So if you calculate this one, there are 50 data of iris setosa. We have also 50 data of iris versicolor, and we have 50 data of the iris virginica. This is in the bar plot because we don't have any categorical data. You already see the distribution. Okay. So the distribution here, yeah, you can select the bin width and the fitted distribution. Here the fitted distribution means you want to see whether the data is in the normal distribution or in other distribution. So if you are learning the statistic, you might understand about the exponential distribution, kernel distribution. Okay, so you can look at this one: gamma distribution, Rayleigh distribution, Pareto distribution, exponential kernel density. Okay, but of course, yeah, it is yeah, its distribution, they have their own definition. So with this kind of distribution, you can look at your data, whether it is in the normal or not. First, I do not want to discuss about this one, but let's just focus on the data visualization. This is histogram. Why? Why is it histogram? Okay, correct. Because it is continuous data. You can see the sample length is numbers, numeric. And we can select the bin width. If it is 0.2, then it will be every 0.2. If we set into 0.5, then it will be every 0.5. Okay. So we call this is the histogram. What about the other graph? Scatter plot. Okay. We just look at the scatter plot. I do not see. Okay, let me just remove the color. Okay. If you want to show the color, yeah, we can see this color. Okay. The size. So if I want to see the petal length and the petal width, this is the data. And we can have also another thing. We call it the size. So you can select the third variable. Okay, as I mentioned before, when a third numerical variable can be added, it creates a bubble chart. So this, I would like to add the sample length, for example. You can see there is a difference. Okay, the different size means this shows a small sample length. Okay. And this shows a bigger sample length. So we have three variables in this scatter plot. Okay, next is about pixel oriented. I will explain this one in this pixel oriented. Pixel oriented, it refers to color or images. If we have this data, income data. So when the pixel is a little bit too wide, it represents low income. If it goes to dark or black, it is high income. So the value in between, it goes from low income to high income. So from this data, we can see the distribution. Seems the distribution is still good. But the credit limit is shown a little bit different. When it is the low credit limit and this is the high credit limit, there are more white than the black. So it means maybe the credit limit is likely low, not that high. We can see the transaction volume. White, black, white. Okay, then maybe this is showing that more likely the transaction is in the middle, not this and not this. Heat map is one example. We can see more obvious. For example, this is about temperature. Average monthly temperatures at Central Park, New York. So we know that in New York, I think it is the same with Korea. In January, it is winter. In July, August, it is summer. So the green color shows the temperature is very low. And the red color shows the temperature is high. Then the red color here, we can say it is higher than the years. So in 2009, I think the heat is not that high, but in 2010, 2011 is hotter than the other years. So with this heat map, we can make a grid of two numerical variables or two categorical variables. We can also plot with the categorical variables. The third variable, it can be encoded as the color of the cells. So if you go back to the orange, you can make a heat map. You can search heat map. So this heat map will show you which one is very low and which one is very high. How do you distinguish the high and the low measure? You can see from this color. The blue color shows 0.1. So it is the small value. And the yellow color shows the high number. So it is the high value. Then I can say that, okay, this is small value. This value is more yellow, then it is high value. If it is green, it is in the middle. Okay. The other kind of things for this pixel, we can see from the maps. Usually we can put in the maps like this one for the spatial patterns. Okay. Spatial means the geography or Earth. We can have the place, X, Y, longitude and latitude, or we can have address, we can have place name. So for example, this one is the statistics of the number of vehicles per 1,000 people in 2015 in USA. So the dark color means the high number of vehicles, and the green color or the light green is less number of vehicles. We can see easily that this area has more vehicles than the other area. We call this is choropleth. Okay, I think I will stop here.